Hello everyone! Today we will prove Cesàro mean in three different cases, namely when the limit a of the sequence an is a finite number, plus infinity or minus infinity. Let's start by considering the case where an converges to a finite number. First, let's discuss our proof strategy. Since we want to prove that this geometric mean also converges to a, it is equivalent to showing that their difference converges to zero as n approaches infinity. This, in turn, is equivalent to the absolute difference of them converging to zero. Okay, so we write this down again here, and we further expand this expression. We can then apply the triangle inequality to break down this expression by two parts. As you can see, the numerator of the left one involves the sum of the absolute difference of a1 and a up to an and a for some integer n. The other one involves the absolute difference of an plus 1 and a up to an and a. In order to use the epsilon n definition, we further aim to make this expression less than some multiple of epsilon. Let's analyze how. Clearly, the numerator of the left expression, being the sum of n finite numbers, is still finite. As the denominator is n, it's clear that the entire expression tends to zero as n approaches infinity. So we don't need to worry about the specific values of the finite numbers in the numerator. We know that when n is large enough, this entire expression must turn to zero. Moving on to the second term, since we know that an converges to the finite value a, again we know that when n is large enough, the distance between an and a must approach zero. But how large should this n be? We can simply let it be greater than the capital N we just mentioned, such that when n is greater than capital N, the absolute difference of an and a is less than a given epsilon. So we keep writing in a more compact way. So they're less than this, and this entire expression is less than epsilon plus epsilon, which is 2 epsilon. Thus, the proof strategy for this part is clear. Now let's proceed to write a formula. Given any epsilon greater than 0, since we already know that an has a limit a, according to the definition of the limit, we know that there exists an integer n when n is greater than this capital N. The absolute difference of an and a is less than epsilon. We also have discussed that the limit of the left term goes to 0. So there exists a term in the sequence. Let's call it the n sub 1th term. At this point, let's assume n sub 1 is greater than n, such that after the n sub 1th term, in other words, for n greater than n sub 1, this term is less than epsilon. As long as n is greater than capital N sub 1, the expression that we wrote holds true. This implies that the limit of the geometric mean is equals to a. Next, let's consider the case where an tends to plus infinity. According to the definition of limits, we aim to prove that as n approaches infinity, this geometric mean is always greater than a sufficiently large k, leading to divergence to plus infinity. However, it's worth noting that this type of divergence, unlike the divergence of a sequence like minus 1 to the nth power, exhibits better analytical properties. This divergence to plus infinity essentially means that when n is sufficiently large, all terms of the sequence fall into some neighborhood of positive infinity, resembling the convergence of a sequence to a finite number. Let's break down the proof strategy and write this down. So we again split it into two parts. We further ensure it is greater than a given k. In this case, we can first ignore the first term on the left side. Note that for index k greater than some capital N, ak will certainly exceed some given value. Let's call it k sub 1, thus is greater than this. Due to the sign-preserving property of limits, it's clear that when n is greater than some capital N, the left term tends to 0, ensuring it is greater than minus 1. The term n minus capital N over n, on the other hand, allows it to satisfy being greater than 1 over 2 simultaneously. At this point, guess what? We can equate the entire expression to the k that we mentioned earlier. Solving the equation, we obtain k sub 1 equals to 2 times k plus 1. This summarizes the main idea. Let's formalize the process. Given any k greater than 0, we know that an diverges to plus infinity. So there exists an integer capital N such that when n is greater than this capital N, we have an is greater than 2 times k plus 1. Also, the limit of the left term that we have just discussed about goes to 0, while the right one goes to 1. So there exists an n sub 1 greater than 0, such that when n is greater than n sub 1, this geometric mean is greater than minus 1, and n minus capital N over n is greater than 1 over 2 is what we have discussed. Now we just have to assure that n is greater than the maximum of n and n1. The expression we've written holds true. Without these, we have proved that the limit of this geometric mean is plus infinity, which is just a. Finally, since we have covered the case where a is plus infinity, the case of minus infinity is similar. We can transform this case into the plus infinity case. When a equals to minus infinity, it's clear that the sequence minus an diverges to plus infinity. Following our previous discussion, minus a sub 1 minus a sub 2 minus on and on minus a sub n over n also diverges to plus infinity, which equals to minus minus infinity. Removing the negative sign on both sides, we arrive at the conclusion. One last reminder. The reason we only discussed these 3 cases, not the scenario where the sequence diverges to infinity, is because such a conclusion may not necessarily hold. Note that this isn't plus infinity. For instance, consider the sequence 1 minus 1, 2 minus 2, 3 minus 3, and so on, where although an diverges to infinity, the subsequent of the given geometric mean, 1 over 2n sigma ak, k from 1 to 2n clearly converges to 0, since each term equals to 0. As per the properties of sequence, the limit of this geometric mean is not infinity. That concludes our discussion for today. The above is the proof of Cesàro mean in 3 different cases. Thank you, everyone.